I've never seen such a
welcome to the last talk of today. Bring some energy after the break. And we're going to have the last talk about zero knowledge, and Nick is going to tell us about zero-knowledge PCPs.
Thanks, Gail. Thanks, everybody, for staying until 4 p.m. Hopefully, this will be, light and fun so that, everybody can wake up a little bit. So today I'm going to be talking about a couple of works with Tom Gurr and Jack O'Connor, who are at the University of Cambridge, on zero knowledge for PCPs. So this is a talk about zero knowledge and actually zero knowledge. It's
Everybody needs to add this.
Yeah, it's real zero knowledge, in the traditional sense. Okay. So I think we haven't actually had a definition of PCPs yet, so I think this might be the first PCP talk. Let me tell you what a PCP is. We have an NP language L, right, and a verifier who wants to know whether X is in the language L. This is the same in every single talk. And the way that he's going to check this is he's going to be given this long proof string pi. And he has a certain kind of access to this proof string. He has basically local access, right? So he can choose some positions in this proof string at random and query into them. Okay. So the completeness property just says that if X is in the language, then there is a proof string that will make you accept. Let's say with probability 1. And soundness. So if X is not in the language, then no matter what proof string I write down, with probability constant over the verifier's randomness, the verifier will reject. Okay, so that's what we're targeting. So there are some important kind of efficiency parameters for PCPs. One of them is the proof length, and in the context of this talk, we're going to just think about we want the proof length to be polynomial. Okay, so we want to be able to write this down efficiently. The other important parameter for us is the query complexity. So this is the number of positions that the verifier looks at when it's checking the proof. And typically, the query complexity will be much, much less than L. So the sort of PCP theorem, the famous PCP theorem, says that for every language L and NP, there is a PCP for this language where the length of the PCP string is polynomial, and the number of queries that the verifier makes is order 1. I guess I missed out something here. So the other thing that we need to pay attention to is the size of each symbol in this string. So in the PCP theorem, the symbols are constant size. So you can think about them as just being bits. Okay. So that's a PCP. What does it mean for a PCP to be zero knowledge? So to get zero knowledge, we're going to want to rather than thinking about a single proof string, we're going to want to think about a distribution now of proof strings. Okay. So this is kind of, think about this as there is an honest prover that is generating the proof. It is randomized, and it's generating a distribution of a proofs. What is the property this distribution has? So I think about any kind of malicious verifier. And the malicious verifier doesn't have to behave like the honest PCP verifier. In particular, it can query in different places and many more places. It can kind of do whatever. And what we want is that the view of this malicious verifier is simulatable. Okay, so there is a probabilistic polynomial time simulator which does not know the sort of witness, right? So it's computationally bounded. It only knows the instance X, and it simulates the view of this V star. Okay, this picture, as I've drawn it, if we have no restrictions on V star at all, this is kind of trivial, because you can imagine that V star kind of reads the entire PCP string, and then, because there's no CRS or anything, we just can't have any kind of zero knowledge guarantee for non-trivial languages. So what we will require is that the number of queries that this V star makes is limited, is sort of a priori bounded by some number B. Okay, so V star can make any set of queries at once, it just can't make too many. And we're going to want this B to be like as big as possible. In particular, we're going to kind of focus on the case that B is like much bigger than the honest query complexity. And like I said, this is trivial if B is bigger than the length of the proof, because there's nothing you can do to simulate. Okay. And like in the standard zero-knowledge setting, you can talk about perfect statistical computational zero-knowledge, depending on the quality of the simulation. The constructions that I'll present today achieve perfect zero-knowledge, so I won't really bother talking about the other two. Okay. So that's the definition. Now I want to give you like a sort of an easy example of a zero-knowledge PCP for NP that has like a weak zero-knowledge property. Okay. So we know that it is hard to approximate the 3-coloring problem in the following sense. So if you're given a graph G, which is promised to be in one of these two cases, either G is 3-colorable or every 3-coloring of G has like 1% of its edges monochromatic, right? Distinguishing between these two cases is NP hard. Okay? And so if I want to design a PCP for NP, I just need to design a PCP for this problem, this like promise problem. Okay? And so here is how I design a zero-knowledge PCP for this promise problem. It's based on just this GMW like interactive proof for NP. So I take my graph, right? This is my 3-colorable graph, and I just permute the colors on the edges. Okay, so I apply some random permutation of the colors, and then my PCP is just this permuted coloring. Okay, so I can think about this as like I take my graph, which has this coloring, and I just cover up all the colors. Okay, to verify, I follow the GMW verification, so I choose a random edge, and I accept if the endpoints of that edge have different colors. Okay, and this corresponds to like 2 queries to this PCP. Okay, so this is a PCP, right? So it has 2 queries, and because of the guarantee about the promise, right? In the no instance, with probability 0.01, I'm going to see a monochromatic edge, no matter what coloring is written down. Okay, and it's also honest verifies zero-knowledge. Okay, so what do I mean? Basically, like if you do as I say, right, if you actually just query like the endpoints of a single edge, then what you will see is just 2 uniformly random different colors, right, in the yes case. Okay, so that's easy to simulate. Okay, so this is not zero-knowledge in the sense that we want. In particular, if I lift 2 hats that are not on an edge, then maybe I see 2 colors that are the same, and now I know that in this coloring, the 2 colors are the same. This is no longer something I can simulate, right? No matter what permutation I apply, I will always see the same 2 colors, 2 colors that are the same on a non-edge. I may see 2 colors that are the same on some non-edge. Okay, so this is honest verified zero-knowledge. It is not, zero-knowledge in the sense that we want for even 2 queries. Okay, so the goal is going to be to like improve this, right? So we're going to try to get this zero-knowledge guarantee for as many queries as we can. Okay, so what was known prior to our work? So there was the original kind of paper that introduced zero-knowledge PCPs was KPT-97, Killian, Petrank, and Tadish. So they have a PCP for NP with polynomial proof length, polylogarithmic query complexity, statistical zero-knowledge, and this query bound can be any polynomial. Okay? So what I mean by this query bound is any polynomial is that kind of first you set the query bound B to be some polynomial that you fix, and the proof length will be some polynomial in that. So that's the sort of order of quantifiers here. There is one significant drawback of this work, which is that the honest verifier in this KPT construction is actually adaptive. Like it needs to make a query and then based on the answer to that query decide what the next query is. This is kind of a weird property in PCP land. It doesn't happen that much. It also means that techniques that we will use that kind of go from polylog query complexity to constant query complexity, they don't apply to this because they only work for non-adaptive PCPs. Okay, so in order to kind of try and get past this adaptive honest verify thing, there have been a few works. So this is Ishai, Weiss, and I forget who the Y is. Huh? Yang? Yeah, okay. And so what they showed is that you can get rid of this adaptive honest verify condition, but you lose out in that you no longer have zero knowledge, but you have some witness indistinguishability property. Okay, so you don't have efficient simulation anymore. You have like a different kind of witness, a different kind of knowledge property. Okay, and then more recently, so this is Kamitaze and Mutu and more. So in order to, I guess it's kind of incomparable to the previous things. So their construction gets back the statistical zero knowledge, but it has a relatively high query complexity, and the query bound is like only a kind of, you have the square root n query complexity, and the query bound is only quadratically big. Okay.
So n is the original witness length?
N is the, I think about it as the instance size.
C
is less than 1/2, I guess. I forget exactly what the, sorry? C is a small constant, right? It's like a,
Okay.
yes.
But it's not adaptive at least.
But it's, so it is at least not adaptive, yeah. Yes.
The proof length in all three could be replaced by quasi-linear, I guess? Or
that is...
it's certainly the second one.
Okay, yeah, I don't know. That could be true. This will not be true for our construction, so it might, if that is true, then it's an important point of difference. Yeah, I guess each of these constructions are like different to us in that they're kind of, you take a PCP and then like that already exists, and then you do some black box transformation on it. So our construction, we're going to like build a PCP directly that has zero knowledge. So yes, so we will get, I say polynomial proof length because I'm not worrying about proof length apart from it being polynomial, but it may be that these achieve better proof length than ours does. Okay. So what does our construction get? So for any query bound B, we say that NP has PCPs with perfect zero knowledge against adversaries that make at most B queries. And here B actually can be up to exponential, and the proof length will just kind of scale in that. So the proof length is some polynomial in the original instance size and this B. The query complexity is constant, and the verification is also non-adaptive. Okay. So just putting it on this picture, I have colored things in strategically so that we get all green down here. So in particular, this is kind of the best you can hope for in terms of the trade-off between query complexity and query bound, right? You can get any query bound you want, and you still have constant query complexity. We also get the best possible zero knowledge. The proof length, it's a polynomial, and there is definitely room for improvement there. Okay. Any questions about this so far? I'm very quiet.
We're in suspense.
Yeah. All right. So there was a question at a previous version of this talk asked by Benedict Bunz, which is, why should I care, right? This is like second-hand information, so maybe he didn't quite say it like that, and maybe he didn't say it at all, but, I guess he's not here. Okay, well, in that case, I can say what I want about it, right? So, and it's a good question, right? Like, why should you care? And the reason we were interested in it is kind of, it feels like it's, it's quite a fundamental question about like the knowledge complexity of PCPs in the same way that like zero knowledge proofs in the usual way are like about the knowledge complexity of interactive proofs, right? This is like how much knowledge does a PCP like need to convey in order to convince you of something. I guess another way of looking at it is it's like kind of the best you can hope for non-interactive zero knowledge without CRS. I mean, in some sense, right? Because like, okay, if I don't have a CRS, I need some other way of getting a handle, like, of having simulation, and maybe like query bound is a way to do that. So this Ishaiwais and Yang, they also gave an application which is this like succinct distributed zero knowledge proofs, which is like zero knowledge proofs where you have the help of some servers, some of which may be malicious. So they show that you can achieve this based on one-way functions, and our result actually shows that you can achieve it unconditionally. On the more kind of theory side, zero-knowledge PCPs are like kind of, if you look at them, they're like definitionally like unsound against no-signaling strategies. So they're kind of dual to no-signaling PCPs in some way, because the simulator will kind of generate plausible-looking pseudo-distribution, basically. And this is related maybe to this integrality gets for Shirley-Adams. It's like the same kind of object. And finally, as like a big reach, maybe this has something to say about quantum PCPs, because quantum PCPs, like if you wanted to construct them, one of the obstacles is that kind of quantum codes, like quantum encodings of quantum witnesses, have a local indistinguishability property that mean that, like, if you look at a small sort of set of qubits, then that set of qubits should not tell you anything about the encoded message, because otherwise you would kind of break the error correction property of the code. And what this says is that, okay, that could still be the case, but you can still get some kind of testability, right? So even though the proof does not actually convey any information about the encoded witness, it is nonetheless a testable proof.
Does this last bullet, is it related to efficient simulation, or is the WI notion?
Yeah, so WI is probably enough for this, yes. I would think so. I mean, I guess it's a little bit unclear because I don't know what WI means in the case where you have like one a unique witness, for example, but I think probably WA, yeah. Like it doesn't matter about efficient simulation, really. Yes?
Can you hope to get both, zero knowledge in the limited query regime and then WI in the full reading regime at the same time?
I don't think so. I think probably, I think like once you, like the PCP itself is a witness, right?
WI,
so like,
we know, statistical WI we know nothing about, so that's a big open question.
Yeah, okay, so I don't know, but it seems unlikely that you could get WI in this setting.
Zaps is what is computational, not
Computation, yeah, okay.
Statistical.
Yeah, computational.
Yeah. Also, there's no, like, it's just one message, right? There's not even a there's no CRS or anything, right? It's just.
But you could hope to get computational WI in conjunction with those things.
Yeah, we have one message computation WI.
Oh, okay. So and the way you do it is you start with the witness already in the WI form, and then you run this.
Okay, maybe that would work. Yeah. Okay. Yeah. So okay, maybe you can add that to the list. Good. Okay, so I don't know if I've convinced you to care. If not, then you're welcome to leave, because because for the rest of the time I'm going to be explaining just how you build these things. Okay. But before I do, any questions? Okay.
There's one.
Oh yes. Go ahead.
What's left? Sounds like you just solved the problem completely.
Good, yeah. So I will talk a little bit at the end about some open problems, but one big one is the proof length thing. So I guess I can mention briefly. So this poly here is some poly that is, we don't figure out what it is, but it's probably pretty bad. And ideally, you would like sort of quasi-linear in N, maybe even like plus something that's linear in B, something like that. That might be the best you could hope for, right? Whereas here we have like some polynomial in N and B. It's like, so this is really where the interesting stuff is.
Potentially another question would be a separation between parameters that we know are achievable with non-zero knowledge PCPs, and who knows, for some fundamental reason are not achievable with zero knowledge.
Yes, yes.
But I'm not sure whether that's plausible. It seems like we can shoot for everything that's achievable with PCPs. We could potentially.
Yeah, that's my feeling at the moment. But actually, I guess it's not clear what the best kind of relationship between proof length and N and B should be, right? So maybe there is some sort of fundamental limit of like how zero knowledge, like how big B can be as a fraction of L before you no longer have zero knowledge. I don't know. Okay. Good, so that's why you should care. Great, okay, so let's talk about how we build these things. So we're going to start from like the very classic template for building PCPs. So I have some NP relation. Okay, I'm going to be talking about relations rather than languages just because it's easier to have the witness around. So I start with some NP relation R. I have this, I want to prove that there is a witness such that XW is in R. And here is how I do it using a PCP. This is like a very, this is a sketch, but this is broadly how it's done. So first you take your witness and you encode it with some locally testable code. Okay, for example, the read-muller code. And then you say, okay, now I have this encoding. I'm going to attach to it a proof of proximity for this relation. So it's going to be a proof that sort of the thing that is encoded over here is actually at least close to an encoding of a witness such that XW is in R. Okay? So I kind of break down my problem into these two parts. I encode the witness, and then I prove something about the encoded witness. Yes?
Is the like PCPP for a relation that's defined with X?
Yes, yes. So X, this is like, I guess the relation, like sort of the explicit input of the relation is X, and the like kind of implicit input, the oracle input is this C. Yeah, so X is part of this relation.
So for each X, like a different relation, right? On which you do a PCPP.
I mean, I guess you can think about it like that, yeah. I mean, the way that I think about it is like you have two inputs, right? You have like an explicit input, which is X, and an implicit input, which is the thing that I have a proximity claim about, which is this.
Explicit and implicit input to what completely?
To the like.
The R.
Yeah, I guess the relation is kind of X comma enc of W, right? So where X comma W is in R.
Oh, okay.
Yeah.
Okay.
Yeah. Okay. So this template actually suffices pretty much to get you a PCP with like polylog queries. To get to order of one queries, you do some complicated stuff with proof composition. I will not have time to talk about that today. But the important thing to note is that the proof composition step is kind of where we use the non-adaptivity of the honest verifier for the construction. Okay. Good. So how do we get zero-knowledge PCPs? Well, what you do is you just like put ZK in front of both things, and then you're done, right? Okay. So what? So there's a ZK LTC over here, right? So I guess what we need basically, like here I have kind of two sources of leakage of information about the witness. One of them is I literally wrote down an encoding of it over here. Right, so if you can query this into this encoding and this encoding just has the witness in it, then obviously that's not zero knowledge. And the second part is that I probably have some information in this PCPP about the witness as well. And so I just need to hide information in both parts. So on the left, I'm going to replace this encoding with what's called a zero-knowledge LTC. And then on the right, I'm going to have a compatible zero-knowledge PCPP for this, so now this encoding here is the zero-knowledge LTC encoding. And then if you want to go to order one queries, then you use proof composition, and we show that this kind of, you don't really need to change anything here. Like if you have a strong enough zero-knowledge property here, then you get a zero-knowledge property here as well. Okay. So now I'm going to talk about these two objects, the zero-knowledge LTC, zero-knowledge PCPP, and I'll show how we kind of stick them together to get the final construction. Okay. So zero-knowledge codes, these are a really fascinating thing. I think they've been rediscovered like 4 or 5 times or something. They're like very interesting, and there's a bunch of different names for them. They have applications in secret sharing and learning theory and things like that. So it's good to know about them. So what is a zero-knowledge code? So we have some code C. This is my code C. And I have a randomized encoding function. Okay, so it takes in a message M in 0, 1 to the K, and it maps it to some code word in C. Okay, but it's randomized, so there's some randomness here. It's not a deterministic map. This encoding function has the property that if I look at most B positions, this B here is the sort of the zero-knowledge parameter of the code. If I look at most B positions of the encoding, then the marginal on those B positions looks the same as if I just encoded 0 under that function. Okay, so it doesn't reveal any information about the message. Okay, and if C is also locally testable, then we say it's a B zero-knowledge LTC. Okay, so it's just, it's a zero-knowledge LTC is just a zero-knowledge code that is locally testable. So in our construction, we will get B being like L to the epsilon, where L is the length of the. Okay, so it's going to be some sort of inverse polynomial, like some nth root of L.
Oh, so you actually construct this thing?
Yes, so we construct one of these things.
Because it wasn't.
It was known before, but we need a particular kind of thing for our construction. Yeah.
I see.
Yeah.
And you're hoping that the resilience, the zero knowledge holds for a B that's larger than the local testing.
Yes.
Query
Yes.
complexity.
Exactly. So yes. So we will. I'll explain this, but yes. Yeah, so it will be important that this B is larger than the query complexity of the local tester.
This is for any A or for bounded A? Or?
Any A, yeah. I didn't need to put the A here. It's more like it's a statistical statement, right? It's just, for symmetry with the other pictures. Yeah. But you can just say like the restriction to S, to any set S that is of size at most B is like the marginal on that looks the same. I did have a slide actually with like a bunch of math on it that had like a bunch of different interesting equivalent definitions of this thing, but I thought it's probably too late in the day for that. So, okay. One interesting thing about these codes that is of interest to me is that if this B is like omega of L, then actually a good like omega of L zero-knowledge code is also a good quantum code. Via the CSS construction. So there is like a very natural way to build a quantum code from this object. And it almost works in the other direction as well, not quite for some technical reasons, but they're very related things. Okay. Any questions about zero-knowledge codes? Okay, so that's the first component. The second component is what I said is zero-knowledge PCPP. So I'm going to define firstly what is a plain PCPP and then talk about zero-knowledge. Good. So we're going to want a PCPP for this relation, right? So this is like x comma c, where c is encoding of a witness for x in the original relation. Okay, and the way that the PCPP works is that you think about the verifier has access to like Oracle access to this C, right? So he can like make local queries to C. And then also he has access to this, to a proof string, which is kind of a proof of this proximity for this R prime. And the soundness is this kind of proximity soundness, right? So it says that if the distance between C and like everything that is a valid encoding of a witness for X is large, then V should reject with good probability. Okay, so we can't get, we can't hope to say, we can't hope to get kind of a precise, like an exact soundness condition because V is only looking locally at the proof. But we can say that, there's, if we're some distance away, then V will reject with high probability. So for the rest of this talk, I'm actually going to ignore this fact. And I promise you that everything works with proximity, but I'm just going to assume that we can really test whether C is in this relation or not. So I'm not going to worry too. I'm going to assume that this proximity parameter is basically 0. Okay. Good. So that's a PCPP. What about a zero-knowledge PCPP? So just like in a zero-knowledge PCP, we have a verifier that is making queries to the proof. But now also this verifier can make queries to C as well. And what is the zero-knowledge property we want? It turns out the right thing is that we have a simulator, which again is PPT, which kind of represents the access to both the proof and C. And the simulator should make a bounded number of queries to C. Okay, so in particular, if V star makes like T queries across both of these objects, then we want the simulator to make sort of some polynomial in T and maybe log of the size of C queries to the C. Yep.
What's the justification to restricting this step when you do auto breaks? Maybe
Sorry, say again.
why do you restrict this step to only make auto breaks?
So this C is in the end going to be part of the PCP string, right? So in the final construction, it will be like part of the PCP string, and so V star will only have Oracle access to it. Right? It's like by the sort of the way that the PCP guarantee works. Right? That's the model. Does that make sense?
Nick, question?
Yes.
So in the past, some zero-knowledge PCPs had this kind of a exchange rate of 1. Like
Yes.
1 query to 1 means the 1 query to the other.
Yes.
So in this case, you're allowing yourself some space.
Yeah, we will allow some slack. Yeah, so
you really have to use.
yes, so the guarantee that we will get will be actually like something like T squared times, I don't know, polylog L. Yeah, so we will actually use this space. Yeah. Good. Okay, so these are the these are the two objects, and now we'll see how you can combine them together to get a simulator for like the construction. So suppose that I have this verifier, right? Now it's making B queries across both the encoding of the witness and the zero-knowledge PCP. And this witness is encoded under a zero-knowledge LTC. Okay, so it's just a hybrid argument, right? So I can't do anything to this left thing because information about this W is in here, right? And so I need to deal with this one first. So I just replace this. So this is most B queries to this guy, which means that I can replace this with the simulator. The simulator, by its guarantee, will make some polynomial in B and log L queries to the oracle. So this is where this queries to the oracle is necessary. And now, so long as this poly B log L is less than B, then I can replace this with encoding instead. And so that means that for security against B queries, we can choose this L to be some polynomial in B. Okay. Any questions about that? Good. All right, so now I will talk. Now I've defined these things and showed how they kind of fit together. I will explain how we build both of these objects. Okay, so the zero-knowledge LTC construction is actually pretty simple. So it's based on the Reed-Muller code. It comes from a work with Ale and Michael Forbes from 2017. Where we needed this for some IOP thing, but it turns out it is actually a zero-knowledge LTC, so it's nice. Okay, so we'll think about the message as being a function from the hypercube with side length k and m variables, m dimensions, into 0, 1, and think about m and k as being like.
Sorry, can I bring you back? Why did you need the local testability for the code?
Okay, good. So for for soundness, right, I want to test that this encoding is actually close to a real encoding.
Did you need it if you have a full-blown PCPP?
Yes, because the proximity, I'm only going to get a proximity statement from the PCPP. I guess if the PCPP includes, let me see. Maybe this is not true, but actually what will actually happen is that the PCPP will prove some statement kind of conditioned on this already being close to an encoding, and then yeah. So maybe the way that I've written it doesn't look like you need it, but you do.
Okay.
Yes. Okay. Good. So okay. So this Reed-Muller encoding, we're going to think of the message as being a function from the hypercube with side length k and m dimensions to 0, 1. Okay, so we just arrange things into a cube, and it's convenient to look at the message like that. So the standard Reed-Muller encoding is just you take kind of the lowest degree polynomial that agrees with the message on the set 1 up to k to the m over some polylog size field, right? And I'm going to assume that f, there's some nice embedding of 1 up to k into f so that everything is okay. Right, so I just fix the unique polynomial that agrees with w on this this set k to that. Okay. So this is not zero knowledge, right? In particular, it's a deterministic thing, so it can't possibly be. So in order to make this zero knowledge, we make two changes. Okay. So firstly, we're going to blow up the degree by 2. So this you need because basically standard Reed-Muller is kind of quite redundant, and so if you have too small degree, then you have too many. There are too many interesting equations that you can find in here that tell you stuff. So we blow up the degree, but that's not enough because even if I blow up the degree, I still have this problem that my message is literally written in the systematic part, right? So I need to make it not systematic, and the way that I do that is I add t variables where t is some parameter that I get to choose. And I basically encode the message as the sum over the last t variables of the big polynomial, right? So I think about, here is maybe the toy picture. So here I had something two-dimensional, now I have something three-dimensional, and I obtain the original message by like summing over one of the dimensions. Okay. Okay. Any questions about this? This is, I guess, the...
Wait, sorry.
Yep.
Is there any insight to the degree? I understand that you have to have degree larger than k, but is there any insight for the 2k?
For the 2k, it's just like what we can prove. Yeah. If the degree is, if the degree is k, then there are things you can do. If the, I don't know what if the degree is like k plus 1. Yeah. So but for 2k we can
Okay.
Yep. Okay. So good. So this is the encoding. What are its properties? Well, firstly, it is locally testable because it's just a read-malloc code, right? It's like a read-malloc code with a weird encoding function. So that's fine. The second thing to note is that it is k to the t plus 1 zero knowledge. Okay, and the intuitive reason for that is that if I want to learn like any w of x, then intuitively I have to like evaluate this sum, right? I have to like did I do this wrong? Sorry, this should be k to the t, not t to the k. Yeah. So this is I have to evaluate b at k to the t points, right, in order to compute this sum. And okay, like this is actually like this intuition is only really true if I like look just inside of the hypercube, but you can show that because of this blow up in the degree, actually it's true even if I allow queries across the entire space. Okay? So in order to learn any single point of w, I have to make k to the t queries. It also has a nice multiplication property, which will be useful in a second, which is, so if B1 is an encoding of W1 under this code, and B2 is an encoding of W2, then I can take some like weird product, right? So I have like fresh variables Y1 and Y2, and I multiply these together, right? This is going to give me an encoding of W1 times W2, but now the extra variables are like 2t. Okay. And you can think about it because like if I have a double sum here, then the sum will distribute over the two copies of the y's. So everything will work out. Okay, so that's the zero-knowledge LTC.
Can you explain again why this is locally testable? Of course you can low degree test, but you're imposing an additional constraint on your code, right?
This thing is actually not an additional constraint, right? So every code word, every read-malloc code word satisfies this for some w. Yeah. So, yes. Exactly. So the image of this encoding map is just read-malloc. Yeah. Good. Okay.
So Nick, if you replace this by different ways of making code zero knowledge, like what's special about this specific way of making read-Muller zero knowledge?
It is compatible with the PCPP that we're gonna do next. Like basically, it's compatible with sum check, right? Because they have this like nice kind of sum checkable condition. Yeah. Good. Okay. Yep.
But you need to test the sum of the b's is less than is in the less than equal to k. It's not a general.
The sum of the sum of the b's is less. So
it is the encoding of say it is a code word.
So it's always a code, like no matter what, right? This is always a code word. It's just I don't know which code word it is necessarily, right?
I guess the way you phrased it before, you wanted w of x to be Boolean value.
I wanted. Okay, this is true. Okay, so ignore this. Assume that I wrote f here.
Okay.
It doesn't really matter. Yeah. Thank you. Sorry, that was confusing. Yeah. So basically, I'm from the LTC side. I want this to be f. Later, it will actually be Boolean, but we'll enforce that in other ways. Okay. Yes.
Is it obvious that you can efficiently sample these random b's given the w?
You can sample them in polynomial time. You can do it. I mean, everything here is polynomial size, so it's like you're just writing down a. It's just like you're doing like an f of t or whatever. Lagrange interpolation. Okay. Good. So now I'll talk about the zero-knowledge PCPP, which is kind of the reason why we needed this special. So there were other constructions of zero-knowledge LTCs before. they don't work for us because we have a particular requirement for the PCPP. So following the classical template of BFL, basically you can reduce testing this property, right, that C is an encoding of valid witness, to a claim of this form. Okay, so we have oracle access to some polynomial P, which is actually composed of some other stuff. But basically, think about I just have oracle access to a polynomial P, and I want to check that the sum of P of x, where x goes over k to the m, is equal to some value n. Okay? That's, I'm not going to explain, like it's kind of standard how you do this, so I don't want to explain it. But basically, we are reducing to this problem, right? And then you may ask, how do we check such a sum, right? I don't know. Any suggestions? Okay, good. So it's sum check. So now that we've reduced this problem to, I guess the important thing here is like the structure of the LTC allowed us to reduce this problem to sum check, right? That's like the magic, right? So we needed kind of that things look like polynomials. We have some summation stuff, and we have this multiplication property, right? And that is what allows us to go to here. Okay. Good. So now we've I want to just zoom in on doing sum check, right? And this is kind of really the technical part. Like this is the most interesting piece of this construction is like how do you do sum check in zero knowledge using a PCP? Okay, so since drawing m-dimensional cubes is beyond my abilities, we're going to focus on the bivariate case. So think about this, we have a bivariate polynomial, and I want to prove that the sum of this k by k square is n. Okay? And here is how we do it in the sort of standard sum check. So what you do is you write down this proof, which I'm going to call sigma p, which is just the sum over each, so you look at the sort of first k columns of this, and you sum over each row, and you write down the sum in sigma p. Okay? And then when you want to check, all you do is you check that this top part here, the first k columns, the first k rows of sigma p actually sum to n, and then you do some random consistency check to make sure that sigma p is actually what it's supposed to be. Okay? So this is, sorry, I should say, so this is saving computation, right, or saving queries, because in order to actually compute this myself, I would need to make k-squared queries, and now I only need to make k. So at least we're doing something non-trivial, even if it's not such a big gap. Okay, so it's plain that this is not zero knowledge, right, because if I make a single query to the sigma p, then this is defined to be like this sum of a bunch of points in the original protocol, in the original p, and so I need to make k queries to p to simulate any one query to sigma p. Okay, so this is the problem that we're going to spend sort of the next 15 minutes trying to solve. So the first idea that we need is something called random masking. And so the idea is to use the random self-reducibility of sum check, right? So in the proof, I get the prover to send me, the prover to write down a random polynomial r, which is sort of the same shape and degree as p, such that this polynomial r sums to 0 over the pink square. Okay. And then I add a proof that p plus r, of like the summation of p plus r, right? This like sigma of p plus r. Okay, and to check, I can do really the same thing, right? I check that this sums to n, which it should be, if this is indeed summing to 0, then this should also sum to n, and then I check consistency across now just these two guys. Okay, so it's still k queries. Completeness, okay, I just did it. And zero knowledge is actually not too difficult to see, so I'll just show it. So this is a zero knowledge something. I hesitate to say proof, but it's a zero knowledge something. The way that we do simulation is kind of nice. So this is the real proof, right? It's like an R, and then we have this like summation of p plus R. So what we do is in the simulator, we choose a Q uniformly random that sums to this target n. And then we write down sum of Q. And then whenever so we can answer queries to this sort of summation part just by, answering, like coming up with, writing down sum of Q. and this doesn't require any queries to P. The only time we need to query P is when the verifier queries in this part, and this I can answer by just Q minus P. Okay, so this is the simulate. So this actually gives you this like one-to-one trade-off.
Wait, sorry,
Yep.
I missed the soundness part.
Ah, good, yes. It's not sound.
Oh.
Yes. So probably as you observed, it's not sound because I have no idea whether this thing sums to 0, right? Yeah, so the prover could just lie to me about this. Good, okay, so let's try and fix that. Okay, and one way you might try and fix that is you say, okay, well I have like a way to prove that things sum to 0, right? I use sum check, okay? And now, the verifier checks that the sum of P plus R is n, the sum of R is 0. So now it is sound, but it is not zero knowledge, right? And the reason is that this sigma thing is the linear function, right? So I can just subtract this from this, and I get back sigma p, and that was not zero knowledge. Okay, so that didn't work. But something very similar will work, and it's kind of weird that it does. So here's what we do. So rather than doing like both sums in the same direction, we use the fact that the sums are like symmetric up to under reordering of variables. And so we do this sum over the rows and this sum over the columns. Okay? Since decent smile, it's silly, right? Formally, right, if I write RT, R transpose to be just like R, but with the variable swapped. And then sigma of R transpose is just it's just the sort of sums over each of the columns of this R. Okay. So to check it, I just check now both proofs, and I do this kind of cross-shaped thing to check consistency. And it turns out that this is complete and sound, and it may even be zero knowledge. Okay. So. Good. So we will spend, I guess, the rest of the time trying to figure out whether it is. But hopefully it's clear that, like, at least the this kind of linearity attack is now broken, right? Because we've kind of, by switching the order of the variables, now this is no longer linearly related to this thing. Okay. So before I talk about zero knowledge, I want to make like a small change that makes things easier to talk about. So rather than having these two proofs, like for R, but P plus R and R transpose, I just want to prove like one thing for this like P plus R minus R transpose, right? And notice that no matter what R is, if I sum over over A and B in K, right? If I sum over any symmetric set of RAB minus RBA, then they're going to cancel out, and so this sum will just be the same as the sum of the PAB. Okay? So actually, I don't even need R to sum to 0 over the pink part. Okay, so we're going to look at this proof system, and yeah, so the checking is just the same. Now we need to check, because we have this R and R transpose, we need to check like this part and this part, but it's more or less the same. Okay, so why might this be zero knowledge? So let's focus now on the combinatorial structure, right? So this is like just zero knowledge in the K by K the little square in the top left. Okay. So if I just look in that square, right, then what I see is that this R minus R transpose, which I'm going to call A, is a random antisymmetric function. Okay, like it's R. If I look in the top in the K by K square, it looks like a random function. I subtract a random function from its, a random matrix. I subtract a random matrix. I subtract the transpose of that matrix from itself, and I get a random antisymmetric matrix. Okay, so it's like some lower triangular L and then minus L transpose, okay, and then zeros in the diagonal. So that's what this looks like when I restrict my attention to this K by K part. Okay. So now let's say that the verifier comes along and queries sigma p plus a at some point gamma. So what that looks like, right, is that it's going to be a sum over p and a sum over a of the same row. And if this is the first query I've made, then this is just going to be uniformly random over the field, right? Because this is like this black stuff is all random field elements. So this will just be uniformly random over the field. In particular, if I wanted to kind of figure out from this gamma what this sum over p is, then I need to like subtract off everything in here. And that means I need to make k minus 1 queries, right? This one I know is 0, and I need to like subtract off everything else in this row. Okay? So the simulation strategy, whoops, sorry, okay, let me just, I need to subtract off everything in this row. I could also, you know, try and make use of the antisymmetric structure in this matrix, right? Because this row is the same as this column, right? Because it's antisymmetric, or maybe minus this column. And so I could also look at this column, but I still need to make k minus 1 queries to this column in order to figure out, in order to subtract off this thing. Okay? So the simulation idea will basically be, I try and just keep track of like when I have managed to remove this mask, right? So when, you know, the verifier, when he's querying, he builds up sort of linear equations that look like this. And I just need to keep track of when he's made enough queries to certain areas of the proof to like subtract off this thing, right? And then at that point, I'm on the hook to sort of query p and figure out what this row sum is. But notice that this only ever happens after I've already made k minus 1 queries to here, right? So k minus 1 plus 1 is k, and so I have enough budget to query all of this stuff. Okay, good. So that was the combinatorial part. Now, you know, obviously there is not just the combinatorial part, right? In order to like have some soundness, I need to look at the low degree extension. Okay? And here things become a little bit tricky, and actually we don't know how to analyze precisely the construction that I described. So in f cross f, like over the whole field, this looks like basically it's a random antisymmetric polynomial. Right, like it still has this antisymmetric structure, but this is no longer just like an arbitrary random matrix. It also has this kind of low degree structure that's, more difficult to work with. And actually, this is like too much structure for us. We don't really know how to analyze this. Like probably the antisymmetry and the low degreeness interact in some weird way. And maybe if I were a mathematician, I would know, but I don't. So what we do is we take the sort of computer scientist way out, which is we simplify the problem. So we notice that actually you don't really need the antisymmetric structure outside of this top left square, right? So why don't I just get rid of it outside of this top left square and make this thing as random as I possibly can? Okay. And so what that means, what as random as I possibly can means, is that I will add to this A, right? So this A is like R minus R transpose. I will add a uniformly random low degree extension of the function that is 0 on this part, right? And this will give me basically like as random as possible a function here that is still low degree and is antisymmetric on this top left. Okay. Now you may be asking, okay, the prover is going to write down this uniformly random low degree extension of the 0 function. How can I trust that it's actually 0 on the thing? We're not. We're just going to use some facts about polynomials. So rather than writing down random low degree extension of the 0 function, what you can do instead is you can use this combinatorial Nullstellensatz. So any low degree extension of the 0 function will factor into two parts, or I guess dimension, like number of variables, many parts. Here it's 2, where this here is the polynomial, like a univariate polynomial that vanishes on the set 1 up to k, and then we multiply that by some bivariate polynomial, and the same in this term. And it turns out that if I choose tx and ty to be uniformly random of the appropriate degree, then this whole thing will be a random low degree extension of the 0 function. Okay.
So the vx and vy, they're kind of given.
Yeah, I mean they're easy to compute, right?
Yeah,
like yeah, exactly. Yeah. So the
okay.
verifier will compute these,
Yeah.
right? And the prover will provide tx and ty. Yeah. And it doesn't matter now what they are, so long as they're polynomials. Okay. So once we do that, then A is going to be like basically a uniformly random low degree extension of an antisymmetric matrix. Okay? And it turns out from some work of Aronson and Vigdisson and prior work from us that you can simulate T queries to this whole A using T queries just to entries of M. Okay, so if I give you a random low degree extension of and in fact, the antisymmetric doesn't really matter. If I give you a random low degree extension of a function, then you can kind of simulate oracle access to that using a small number of queries to the just the systematic part. Okay, and that finishes the bivariate construction. Okay, so the structure of this PCP looks like this, right? So this is our P that we are trying to prove sums about, and then we have the random R, which is we add it here and then subtract its transpose, and then we have Tx and Ty, which form the parts of the extension of 0, and then this A is going to be this kind of composition of all of these things, and then we add like a sum check proof for just P plus A. Okay, so that's the bivariate case. The multivariate case looks very similar. So now we have m variables, and it turns out that the right thing to do, the sort of right version of this transpose, is to just like reverse the order of all the variables. Okay? Sorry?
Just once?
Yes. Yes. Yep. So there's still just two terms. It's just like now I just reverse the order of all the variables. So the only thing that really becomes more complicated is that now this like low degree extension of 0, because there are m variables, it now has m terms, so I have m of these t's. Okay, and then I guess the sum check proof also looks more complicated, but now so in the sort of multivariate sum check proof, we don't have just one sort of column, right? We have like this is the sum over all but one of the variables. This will be the sum over all but two, and so on all the way up to the top. Right, so we have this kind of tower of sums. The completeness and soundness is really just the same as in the bivariate case. Like this thing will be identically 0 when I sum it over everything. So really, it's just the zero knowledge that we have to worry about. So zero knowledge becomes somewhat more complicated, and I guess in the last couple of minutes I'll try and give you a flavor of what it looks like. So now I don't just have like queries to sort of the mask and also like one layer of sums, but I have like multiple layers of sums, right? And each of these kinds of represents, I'll say that in a sec. So the question is like, when do we need to query this P in order to answer queries to pi, right? We like, before we were able to give like a reasonably clear condition about when I've kind of solved enough linear equations to figure out entries of P. Now I have like a much more complicated looking thing, and so I need to understand like when do I need to query this P in order to answer queries to the proof, and I need to know that I don't have to query it too often, right? And the way that we show that you don't is that we look at kind of the structure of what does this sigma A tell you about A, right? Sorry, I should say, so here we had sigma P plus A. I'm just going to ignore P for now. Let's imagine that it's 0. It doesn't really make a difference. Okay, so what does like sigma A tell you about A? And if I just look at the again the combinatorial part, then if I query into the sigma A, then this will tell me like kind of the sum over some like facet of this hypercube, right? So I will get like a bunch of sums over facets of this hypercube, or subcubes of this hypercube, and the subcube here is like basically everything in the hypercube, right? The evaluation of A on everything in the hypercube that starts with some prefix little a. Okay, so I can get like any sum of this form, right? I can get a sum over any subcube where like we have a fixed prefix. Okay. So T queries to sigma A corresponds exactly basically to T subcube sums. Again, this is just in the combinatorial part. I won't have time to talk about the kind of algebraic case. Okay, so to understand what's going on here, I'm going to define the set rev of S, which is so I take every point in S and I write down its reversal. Right? And the observation is that if I have this kind of anti-symmetric function on this hypercube, right? So this is going to be like R minus R transpose. This is identically 0 when I sum over a set S, if and only if S is symmetric under this like reversal, like it's invariant under this reversal operation, right? So this is like a generalization of the, the dual of a antisymmetric matrix is a symmetric matrix. Okay. So what we show is that for sets of this type, right? So if S is here is a union of subcubes, and I'm assuming here that the disjoint, this is something you can deal with. So if S is a union of disjoint subcubes, you can ignore this. And S has this property that it's equal to its like reversal, it's invariant under reversal, then S is either really small, like it's of size like polynomial in T, it's like almost nothing, or it's really big, it's like k to the m, it's like everything except for some small number of points. Okay? So like if S is kind of a dangerous set in the sense that like I can remove this mask, then S has to be really small or really big. Okay? This means that actually we're good, right, at least in the combinatorial case, because if S is really small, then I can query every point in S, and I can compute the sum over A of X of S easily. Sorry, the sum over P of X of S. And if S is really big, then here again, I just need to compute the sum of P of X over S. I know the sum of P of X over everything, right? And so I just need to subtract away the points that are missing. Yeah. Okay. And the proof is actually kind of cute. Like you basically double count the size of S as like S union its reverse and S intersection its reverse, and these should be the same. Probably given this hint, you could go and figure it out if you wanted to. Okay. So it is time for me to wrap up. So like I said, we get zero-knowledge PCPs for NP with polynomial proof length, constant query complexity, polynomial query bound, perfect zero knowledge. We also get the same thing for NEXP with exponential proof length now. And because the proof length is exponential, actually the query bound, you can make it exponential, and then you can say like it's unbounded queries, right? Because no polynomial time adversary can query the whole proof. Interestingly, so in the PCP setting, like NEXP is easier than NP because, in the plain PCP setting, because somehow scaling down is hard. Here, NEXP is kind of harder than NP because you need like really very efficient simulation, right? You still want a polynomial time simulator. And so like everything that I described, all of the kind of simulation algorithms I described now has to work in kind of polylog in the size of the object time. And this is actually pretty hard, and we work quite hard to get that. There's some very interesting algorithms there that I don't have time to talk about. Okay, so future directions, as I said, like the proof length L is some polynomial in B and N, right? So interesting, and a really interesting question is like how close to B can it be? Like can I query, 10% of the proof and not learn anything? I don't know. Of course, like I had some reasons why you should care. I hope that there are others. If you have any ideas for applications of zero-knowledge PCPs, I would be very happy to hear them. Thank you.
Questions?
Ron.
First, any idea about zero-knowledge IOPs?
So zero-knowledge IOPs are much easier to build. So actually, the idea from this construction comes from a perfect zero-knowledge IOP. Basically, this random masking technique is all you need for zero-knowledge IOPs because you can get soundness by doing a random linear combination of the polynomial of P and R, right? You do like P plus alpha R, where alpha is a random thing. So like the whole difficulty in PCPs is that we don't have that.
Specifically, the sum check is...
Yeah, so the sum check part is that, yeah.
So the constant query complexity you get from the standard...
Just from the standard machinery of like...
preserve zero knowledge?
Yeah, so you lose a bit, right? But the point is that like when you do proof composition, you're basically like you're proving things about the verifier, which is a local operation on the proof. And so you only lose in like the query complexity of the verifier, which is polylog, so it's...
Do you get anything that scales with n time t, or is it just...
It's a very good question that Ale has asked me. So I believe you can do it. We don't, yeah, probably you can. The way that we wrote these things, actually, like there's like two regimes, there's like an NP and a NEXP regime, and the proofs are not the same, but I'm sure you can do something. Yeah, Eva.
So I probably knew the answer to this question and forgot, but in terms of feasibility, zero knowledge versus soundness and stateful versus stateless, right? So PCP is like a stateless prover.
Yep.
And so here you make the prover stateless, so you're making soundness easier and zero knowledge harder.
Yes.
Is there a meaningful, stronger notion where soundness is against stateful and zero knowledge is against stateless?
I mean, I guess maybe like the zero knowledge IOP is kind of this, right? Like, because you have the definition there is you have an IOP, right? But then I'm allowed to like make as many queries as a bounded number of queries to the thing.
Yeah, but in the non-interactive setting.
In the non-interactive setting, I don't know. It's a good question.
Did you want to ask? I'll go after
You go first.
Okay, so I'm trying to understand kind of the nugget here because, people tried to do zero-knowledge PCPs before. We all had the idea of encoding and doing PCPP because that's an actual way.
Right.
And we all had the idea of, okay, you have to kind of add randomness to the encoding to kind of hide things.
Yes.
So it seems to me like for me and you, I don't know, is the fact that you add actually randomness to the little cube.
Yes.
In a way that you're able to prove using kind of this, this brilliant change of variables, like reversing of variables, that it's all of a sudden zero, so you can kind of map.
Yeah. Somehow, I guess like the concept here is right that you have something that is like you have a like randomness that you're adding, and it's slightly structured in a way that it's like adding the randomness, like your problem is invariant on adding the randomness, right? And so, but like it's like a very small amount of structure so that you don't, I don't know. I'm not sure if there's like a general takeaway. It's like very, I don't know. It seems like everything that we do is like very specific to some check and on the structures of these things. I should say, like we're thinking about how to apply these techniques to like other families of PCPs, like things based on Reed-Solomon codes, and there is like a similar sort of thing. I think maybe the takeaway is like you have, like in some check you have like these degrees of freedom about how you do the proof, right? You can either do the variables in one direction or the other, right? And other proof systems also have this kind of thing, whether you make an arbitrary decision, and so. Maybe this is something you can sort of generalize where there are like two ways to do the proof. You kind of do both and then you combine them somehow.
Maybe another point as well is so if you look back to kind of zero knowledge PCP literature, for a while it was for the most part combinatorial, right? And then when you start having more than one round, somehow. Back then, it was easier to achieve zero knowledge in an algebraic way. Mm-hmm. And I guess you become proficient thinking about these masking polynomials, like injecting randomness, using these vanishing polynomials to carve out the areas where you need to preserve. So I think it was like the thinking of zero knowledge in an algebraic way. Now, with rounds, that's simpler. Mm-hmm. And here there is like additional ideas needed to somehow get back to the original setting of PCPs. But I think this detour was kind of needed because there's like a lot of stuff that one has to understand before you get back to getting rid of rounds.
Yeah, somehow the like thing, like so we had the idea for the reversing the variables in like 2017 or something, and so the thing that actually got us to the result was this work on like arithmetized random oracle model stuff. So there we had to work with these like low degree extensions of the zero function, right? And so that's like I guess that was the like missing piece that kind of got us to this thing.
I see.
Yeah.
I see.
Check.
Let's ask the opposite question of this future direction. If B is small enough, can you kind of prove less linear?
If B is small enough.
Some polynomial.
Sorry, if B is so. What are you thinking about small, like being log or something like that?
Maybe say polylog.
I mean, this construction won't get you quasi-linear in N, right? Because the construction even without zero knowledge is already some big polynomial. But yeah, I guess it does. It gets easier the smaller B is. So probably you could maybe get like polynomial in n, and then I'm not sure. I think you have like some very large blow up in the proof length. I think even if b is small, it's probably you can't really say anything meaningful. Ron, yeah.
Going back to my question from earlier about the model of Zero-Knowledge PCP.
Yes.
It sounds like restricting B star to only make query access is a limitation.
Yes.
And we can apply a lot easier. Right? It would be nicer to be able, the solveness, and everything is that, the PCP is for verifier, but the honest verifier only needs to look at certain bits or whatever.
Yeah.
A few bits, but malicious verifier does whatever it wants. And you can need to be able to simulate it. Maybe the simulator only has oracle access. And you prorate whatever the simulator may look depending on what the adversary does. But in zero-knowledge, we don't want to make any assumptions what these start out, right?
Yeah. So I mean, I think I guess the query bound assumption is like kind of, I agree that it's kind of unnatural, but on the other hand, it's not clear like what other restriction on the verifier you could place, right? Like if he can read the whole PCP, then he has the witness, right?
You know what? Let the simulator have the same access as the verifier. Forget that.
The simulator has the same access as the. Oh, good. Okay, so that.
If it chooses to look only some queries,
yes, yeah. So there we can say something. So we can get PCPs for like sharp P with this property, right? So like we can get a PCP where basically for every query to the PCP, the simulator like does something, right? So if the simulator is like if the verifier runs in more time, then so eventually maybe the verifier does read the whole PCP, but the PCP is exponentially large, and so it's kind of okay. So this does exist, but somehow when there's a witness, like you have to write down the witness in the PCP somewhere, right? And like it's so if you make enough queries, you get it out, right? I mean, okay. So if we're allowed for the PCP to be exponentially large, then this works fine, right? Then I can do it. Yeah.
Okay.
One more question.
One more?
Okay, yeah.
Okay, yeah.
Given how good the parameters here are, is there any reason why we can't have PCP equals ZK PCP? Like in the sense that given any PCP, like you can for a language you can have a ZK PCP with similar parameters.
Yeah, this is a good question. So that's actually like what these previous approaches basically tried to do. So I don't know how you would do that, but this is maybe future direction number 3 is like, is there like a general construction, right, that takes any PCP and gives you like a PCP with similar parameters, but it has these properties.
Okay, with that, thank you so much.
Thank you.
So much.